CIT 1121, Module 11, Submodule 4, Network Segmentation. There's just a couple of slides in this particular video, and it does bring up a very important concept, though, of segmentation. And segmentation is based on the idea that all the devices that are connected together on one side of a router are going to be in the same broadcast domain. So as we look at this, there are certain protocols that are going to use broadcasting as a method to complete a task. For instance, they talk about ARP in here, and they talk about DHCP. Those are the two most prominent protocols. They're like helper protocols that allow you to set up your networks and either, in DHCP's case, give an address to a device that has no address, and a subnet mask, and a default gateway, and a DNS server. Or in ARP's case, identify, when traffic is identified as either local or remote, identify what MAC address you're supposed to send it to. If it's local, send it to the MAC address of the destination device. If it's remote, send it to the MAC address of your default gateway so your router can receive it and then send it where it needs to go after that. So as far as segmentation goes, or broadcast domains, one segment is one broadcast domain. And that's an important thing. And all of the devices that are going to be in that same segment are going to be within the same range of IP address values. And more on IP address subnetting very, very soon. Okay. Problems with large broadcast domains. When you start getting your broadcast domains start to get too large, you're going to send a lot of broadcast messages. That means there's a lot of devices that are going to use these broadcasts to send traffic to a lot of other devices. It could overwhelm the network, and it could create a network that is slow, and your broadcast messages are actually taking bandwidth away from your production network, and that can be a problem. So that's one reason that you would segment down a network and have fewer users. And in this diagram, they're just saying, well, just make them a little smaller. Instead of doing 400 users in one network or one subnet or one segment, let's break it into two parts. Let's make 200 users in this network, so a 200 user broadcast domain on the left and a 200 user broadcast domain on the right, and we'll physically separate them by plugging them into a router on different interfaces, and we're going to put them in two different broadcast domains and two different subnets. So that's what they're getting into on this particular slide. The next slide, they talk about, well, there's other reasons that we might want to segment things out. Some of them, sometimes it's reasons for security or for function. So, for instance, we at the college, we have a public internet that everyone can use to gain access, but that doesn't have direct access to the, say, grading, where the grading system is at. That's on a completely different network, and we're going to set a bunch of rules up that say that, you know what, if you're trying to access the grading system or the network that has grading on it through the public wireless network, we're going to set up a rule that says, no, you just can't do that. You can use the faculty, maybe you can use the faculty wiring to get into the grading system, but not necessarily the public Wi-Fi. So there's a lot of reasons that we can separate things. And keep in mind, if we take something on one network and put it onto a separate network, then those two devices have to pass through a router. And we can set up rules in that router that say, well, I'd like to allow this particular device to have access to this particular service, but I'd like for this particular device or these groups of devices or all these other devices over here to not have access to that particular service. And we can set up these rules in what's called an access control list, and we can make our networks a lot more secure by setting up our systems in a way where we programmatically can control what traffic can get from one segment to another. So that's the idea of what they're getting into as far as segmenting by group or function. You can also segment by device type, depending on how secure your system needs to be. I used to work in a system that was secure enough that all of the printers within the organization or within this particular business group, the printers, they were afraid that the printers could be taken over by hackers, and that hackers could be controlling the printer operating system and stealing information. So you know what we did? We took the printers and we put them on their own separate network, and we only allowed the printing protocol through that particular firewall or router that we had blocking off the printers from the other networks. So there was no broadcasting and no kind of scanning or checking out what else was going on in the network. All the printers were on their own system away from the devices with the secure information. So depending on how secure the network is that you're working on, they could be doing something as structured as even removing printers or scanners or all kinds of devices just off the network. Just get them out of here. That leads us to a big subject that we're going to cover in this chapter or in this module, which is Module 11, Submodule 5, Subnetting an IPv4 network. And in this particular section, we're going to start just talking about some of the things that we've already spoken about, okay? And it mentions here, this is a really great slide. I love the first bullet point. It says, networks are most easily subnetted at the octet boundaries of 8 or 16 or 24. So if you ever see that you have a subnet mask that is 255.0.0.0 or subnet mask 255.0.0 or a subnet mask that's 255.255.255.0. If you're only seeing 255s and zeros in your subnet mask, it means you're subnetting at what's called a octet boundary. And I always say that means you're subnetting at the dot. And that just means that any given value is going to be either on the left-hand side, it's going to be for the network, or on the right-hand side, it's going to be for the host. And in a /8, the very first number of the 4 is going to be to the left, and that's going to be network, and the next 3 are going to be for host. And at a /16, the first 2 numbers in the address are going to be set for the network, and the last 2 numbers are going to be set for host. And in a /24, the first 3 numbers are going to be set for network, and then the last number is going to be set for host. And once again, in a /8, the networks are really, really big. It is a huge, it's 2 to the 24th power number of hosts in a given network on a /8. So that's a lot. That's 16 million. That's written here. In a /16, it comes down considerably. 65,000, still not manageable for a regular LAN. And then for a /24, 254 addresses that are usable that you can have in the network. That's a really much smaller network. And those are the ones we're going to concentrate on mostly in this class, but you can have, like I said, really big networks with these shorter subnet masks. The longer the mask, the smaller the network's going to be. Are we going to go beyond 24? Of course we are. We're going to do that in just a second. Let's look at the next slide. So in this case, it shows us here the first table is for 10.0.0.0 with a /8 and a /16 and a /24. And what it's just showing you here is this, is the first address, the host range, and then the broadcast addresses with the different subnet masks associated. So if you look at, I don't know, let's start over here and say we got 10.0.0.0/16. So how big is that network? Well, the network is going to be 10 and 0 because it's a /16. This is 10, let's write that. It's using a /16, and then there's a /24 in the other table. But 10.0.0.0/16, since the first 10 and the 10 and the first 0 are going to be the network portion. And so everything's going to start. If it's going to be in the same network, it's going to start with 10 and 0. And it's going to go from 10.0.0.1 to 10.0.255.254. That's going to be the whole network. That's 65,536 total addresses. The broadcast address will be the very last address possible in that space. Okay? And that's all they're getting to there. If we look over on the right-hand side, you've got 10.0.0.0/24. Same network ID, same exact starting place. Subnet mask is now greater. The subnet mask says, you know what? It's not the first 2 numbers. It's now the first 3 numbers that we're going to use for the network. So only the 4th number, as it changes, is going to be available for hosts. So these are now only 256 total addresses big. 10.0.0.0 would be the network ID. 10.0.0.255 would be the broadcast ID. And anything 10.0.0.1, 10.0.0.2, 10.0.0.3, so on and so forth, all the way up into 10.0.0.254, those numbers would all be for unicast host values. Okay, so keep that in mind. That's a pretty cool slide. This is more of the same, except for we're just going to go further in and make the subnet mask longer and longer. So as that mask gets longer, you're allocating more values in the address to the host portion. So we're no longer subnetting at the dot. It's not going to be as easy as just looking at the number and saying, okay, these numbers are to the left, they're for network. These numbers are for the right, they're for host. We're going to go into the actual fourth number, and we're going to make networks that are smaller than 256 total addresses. The first thing that we can do in that case is we can do what's called a /25. And a /25 is going to take what was a /24. Let's just do something here. Let's just go /24 up here, okay? And we'll say 255, 255, 255. .0. So this is what we know already, right? Number of subnets is going to be 1. Total number of hosts that we can have is going to be 256. So that's 254 usable hosts, which is kind of the number that they're showing here, okay? When we go to /25, look what happens. We've taken, in the fourth octet, we've taken that number. It was a 0. Now it's 128. How did it get to be 128? We put a 1 in the 8th position in that last octet. And that binary value is 128. No big deal. Now what that's going to do is this. It says this. If that number here in this position is a 0, that's one network. But if it's a 1, it's a different network. And that now we've separated this, what was one network, into 2 networks. A lot more on this later. Each one of those networks is going to have 126 usable host addresses, 128 total. So it'll make 2 networks in the fourth octet. Anything that goes between 0 and 127, that would be one network, because that would have a 0 in that highest order position in this position right here. Or if it had a 1 in that position, then that would be 128. 128 through 255 would be your second network that you would have created. Okay? Hopefully that makes sense, because now we're going to go down to the next one, which is a /26. And look what happens. The number in the fourth position of the subnet mask has now gone from 128 to 192. Well, where did we get 192 from? Because these 2 highest order bits, if you add those together, that's the 128 position and it's the 64 position. And if you add those 2 numbers together, it equals 192. And that's where that number comes from. It's the same thing as where 255 comes from, but we don't think about it that way. We just go, I don't know, it's 255. 255 is 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. It's all of the values added together. They're all 1s, so you 1 it out. It's 255. Easy. So in this case, now we're saying this. We've got 2 digits in the fourth octet that are going to identify the network. Now, that's going to create 4 networks. How does that make 4 networks? Because those digits in the address could be a 0 and a 0, or a 0 and a 1, or a 1 and a 0, or a 1 and a 1. And that gives us 4 different combinations, and that gives us 4 separate networks that could be created. Those would end up being 0 through 63, 64 to 127, 128 to 191, and 192 to 255. All we did here is we took 0 through 127 and we cut it in half, and we made 0 to 63 and 64 to 127. And then we took 128 to 255 and we cut that one in half, and we go from 128 up to 191, and then another 64 address network from 192 to 255. So if you look at this pattern, one network, 254 usable addresses, 256 total. We take those 256, we break them in half, we make 2 networks. Each one with 128 total addresses here and here, depending on the 25th position, whether it's a 0 or a 1. And then we went to the /20/26, where we said, you know what? Not only are we going to check the 25th position, but you got to know we have to match to be in the same network. We have to match it at the 25th and the 26th. They have to be the same number. And each one of these address values, if you look at them, 0 through 63, if you look at 0 in binary, it looks like this. 1, 2, 3, 4, 5, 6, 7, 8. 8 zeros, right? You know what 63 looks like? It looks like this. 0, 0, 1, 1, 1, 1, 1, 1. That's what it looks like. So those 25th and 26th bits are still the same. That's 0, and then that's 63. Hopefully that's making sense. I'm not going to do the rest of them right now because it's way too much. But we have there's a lot more of these, and you'll see them really soon, like later this week.